Welcome back to part 2 of the stress transformation video. So in this part we are just going to be solving for the weight of the sign and the magnitude of the uniform pressure that's applied to the sign, which in this case I'm just going to call it a wind load. So we're going to call it, we want to figure out what the load of the wind is and the weight of the sign. We know that the pole has a 6-inch diameter, and then we know the stress state at point A, so that'll make it a little bit easier. So the thing we're going to have to do is we're going to have to figure out what internal forces are acting at that section cut that's shown below the sign. And so I'm just going to redraw that down here. So we have find forces applied. So give me a second, I'll redraw those. So here's our system redrawn. I'm just going to define over to the right here. F1 is going to just be equal to our weight, and then F2 is going to be equal to our wind load. And so we can simplify that. We saw the uniform pressure applied over the whole area of the sign, and since we know the area of the sign, we can rewrite this as the wind load, which is going to be in units of pounds or kips per foot, or per square foot, and then we'll multiply that by the area of the sign, which is going to be 12 feet by 6 feet, and then we'll convert that into inches, so 12 inches, 1 foot squared, so that we'll get that into an inch. So we know that F2 is just going to be equal to this value, 10368 times wind. So the value we're trying to find is F1 and then technically F2, but we're trying to find wind specifically. So now we can go ahead and we just need to redraw our section cut and then try to figure out what internal forces are going to be acting on that section cut. So our section, if we redraw it down here, going to look a little bit like this. You can say this is our fixed end, and then our point A is going to be located right here. And then give me a second, I'll draw, here we should probably draw our coordinates on this just so we know what direction. So this direction is the Y direction, in this direction is the Z direction, and up and down right here, that is the X direction. So our point A is located right along the Z axis. So first thing we can do is when we move our forces, we can go ahead and move the specific F1 and F2 forces straight onto our section. So F1 is just going to be a compressive force acting right at the centroid. So we'll have F1. We're also going to have that F2 force, which is just going to be a shear stress acting on the system right here. So this is F2. And then now from moving those two forces down to our section cut, we're going to create some torsion and some moments. So we'll start with our F1 force. So moving that F1 force from the centroid of the sign to the centroid of the pole, that's moving it about 6 feet. So that means we're going to be causing a rotation since we have a force acting over a distance. We're going to have a moment created. So if you use the right-hand rule and you can figure out the direction, that it's going to be rotating about the y-axis. So by doing that, we can get a rotation about the y-axis that looks like this, and that's going to be a value of F1 times 6 feet. So that's F1, and then once we've moved F1 to the centroid of the pole, we've effectively taken care of it because now it's the axial forces acting constant throughout the pole. And so now we can focus on F2. So now F2, by moving it from the centroid of the sign to the centroid of the pole, we're causing another twisting action, but in this case it's going to be a torsional twist rather than a moment. And so that torsion is going to be acting around the x-axis. So it's going to be going in this direction, and that's going to be a value of F2 times 6 feet as well. And so now we're not done with our F2 force. We've moved it to the centroid of the pole, but now moving it from the centroid of the sign to our section, we're causing another moment, this one in the z-axis. So it's going to be along this axis. And that value is going to be F2 times 6 feet. So those are all of our forces and moments that are acting on our section. And so now we can write and say, okay, we're gonna have stresses due to axial. So that's gonna be our P over A. We're gonna have stresses due to bending. That's gonna be our My over I. We will also have stresses due to our shear. So that's going to be a VQ over IT. And we also, in this case, have torsion, which is going to be TR over J. So we have a little bit of all of them. We have each stress acting at our point A that we have to consider. So let's start with just our normal stress, these two guys. So we know our normal stress from above. If we look back at our stress state that was given, we know that the stress, sigma xx, is 3.381 KSI. So if we redraw that down here, so our sigma xx is going to be a positive 3.381 KSI. So we know sigma xx, that's our normal stress. That is going to be equal to a combination of axial force and bending. So we can start off with our axial, P over A. We have to plug in a negative in it because it's in compression. Our F1 force is pushing down, so it's causing compression, so that's a negative value. And then we also have plus our My over I. So in this case, we have two moments that are acting, but the only one we're going to consider, or the only one that actually causes a stress at our point A, is going to be our F1 times 6 feet. So this stress right here, or this moment right here. The moment F2 times 6 feet, since our stress point of A is located right along the same axis as it's bending, our Y, or our distance between centroids, is going to be 0. So this one we won't have to consider. So when we're looking at the bending of F1 times 6, so this stress right here, or this moment right here, if we use the right-hand rule to figure out which side is in tension and which is in compression, we can see that when it bends, it pushes this side into compression and the opposite side into tension. So that means it's going to be a positive stress, bending stress, at point A due to that moment. So we're going to rewrite this, and we'll have a negative. Our axial force in this case is F1, so minus F1 over our area. Oh, and then before I go ahead and solve this, we'll have to figure out our area, our I value, and also our J value later on for our stress. So we'll go ahead and do that right now. So our area for this section is going to be pi over 3 squared. So this 3, we know our diameter of our pole is 6 inches, so we know that the radius is 3 inches. So that's going to get us a value of 28.3 inches squared. Our I value for a circle is pi over 4 times the radius, which is 3 to the 4th. So that gets us a value of 63.62 inches to the 4th. And then our J value is 2 times the I value. So that's going to give us a value of 127.24 inches to the 4th. Okay, so now going back to our bending our normal stresses. So that's F1 over our area, which is 28.3 inches squared. And then we have plus our moment, which in this case is F1 times 6 feet. Let's convert that into inches, so times 12. Times our Y value, which in this case is just our radius, so that's times 3 inches, over our I value, which is 63.62 inches to the 4th. So then the only one known that we have is our F1 value, so that means F1, when you solve that algebraically, should come out to being 1.0063 kips, which is also equal to 1,006.3 pounds. So now we can move on to our shear stresses. So our shear stress from above was sigma xy, and that is equal to a negative 5.942 KSI. So our shear stress equation sigma xy. That is going to be our TR over J plus, and in this case, since our shear stress is located at the very max, it's at the centroid perpendicular to our shear force, we can use a simplified equation. Instead of using VQ over IT, we can use 4V over 3A. And that's only when our shear point is at the max shear spot, which is right at the centroid. So we can use that. And so now let's consider if all of these are in positive or negative. So for our we'll look at our torque first. So that torque, if you are to use the right-hand rule and figure out what direction the stress is acting right at point A, you'll find that it's going in this direction, which is the negative y direction. So that means that this stress is going to be negative. So if we are to rewrite, so we're going to have a negative in front of our TR over J, and then for our shear stress, it's acting, if you were to draw an arrow based off of the direction of our shear stress, that shear stress arrow would be going in the positive y direction. So that means we're going to keep it as a positive 4V over 3A. So let's plug in the values. So we have our torque. So we have a negative, and then our torque is going to be equal to F2 times 6. F2 times 6 feet, we'll get that into inches. And then times our radius, which is 3 inches, over J, which is 127.24, plus our 4 times F2, which is our shear force, all over 3 times our area, which is 28.3. So by doing that, we can get our F2. That is going to be equal to 3.6056 kips. And we actually want to find what the wind force is acting on it, not our F2. And so we use that equation that we had solved for before, this 10368 times the wind. And so that gets us a wind value that is going to be equal to 0.3477 psi. So that is the stress that is acting on our wall, or sorry, on our signpost.